Okay, so let's first run through the problem. We have search insert position. So given a sorted array of distinct integers, that could be important, and a target value, return the index if the target is found. If not, return the index where it would be if it were inserted in order. You must write an algorithm of O log n. So the fact that it says sorted and the fact that it tells us to do this in log of n, I think we should automatically think of BST, or at least I do, because binary search tree is essentially cutting the array in half every time, which achieves log of n. I think this is the only way you can achieve it when it's a sorted array. So let's run through an example. We have 1, 3, 5, 6, and the target is 5. So we see that the target is in the array, just visually. And we know it's in the 0, 1 second index. So we output 2. That's pretty straightforward. I'm interested in return the index where it would be if it were inserted in the order, if it were inserted in order. And so on this example, we have 2. And we see that 2 is not in the array. But we can visually see that it should probably or definitely live here, which is technically the 0, 1 index. So we would be shifting all of these to the right, essentially, and inserting the 2 here. So I think that's interesting. That brings a little nice variable into the problem. So I think that all makes sense. All right, so let's run through an example in depth. So typically with a binary search tree, you're going to have a left pointer and a right pointer. And the idea of this is that these pointers are going to represent the array that you're working with. So in this context, we're going to do some calculation. And if it doesn't meet the requirement or the value that we're looking for or something, we're going to continue on the binary search tree. So what does that mean? That means in a binary search, we're going to work with half of the array. So now that we know that calculation is not here, based on a certain criteria, we're going to choose either this half or this half of the array. And then we're going to do said calculation with one of the halves. And if that doesn't work, we're going to run the calculation to another half. And so on until a base condition is met, which is typically when this left pointer crosses over the right pointer, right? That's the gist of a binary search. But the difficulty is typically with one-off errors. And so you'll just have to be a little diligent in how you structure your binary search tree. But let's run through this problem. So we have our left and right pointer and our target is 5. We're going to want to calculate what our middle index is going to be. And for us to calculate that, it's just going to be a pretty simple math formula, which is the left plus the right to get the middle, and divide by 2 to get the middle, and then floor it just to make sure we don't have a decimal place. And in this case, let's run through it. We have our third R, which is 3, and L, which is 0, which are the indexes, divided by 2, which is 1.5. Floor is going to be 1. So M is actually going to live here. Now we're going to say, is the target equal to the value of the M index? No. So let's continue on. How do we know if we want to work on this side of the array and not this side of the array? Well, the hint is that this is a sorted array. It's typically a hint you want to look out for so you know to do a binary search tree, because you can't do a binary search without some sort of sorting element to it. So we're going to say, is 5 less than 3? No. Is 5 greater than 3? Yes. So now we're going to work with this side of the array. And what does that look like? Again, L and R represent the array that we're working with. So in order to work with this array, we're going to want to move L over to M. And that would make sense. It also kind of makes sense that since we already checked that the middle value is not the target we're looking for, we can actually say L can be moved to L to M plus 1, which is here. So now the working array is going to be this. And we're going to run through a calculation again. So 3 plus 2 is 5, divided by 2 is 2.5, and the floor of that is going to be 2. So now m is at 0, 1, 2, which is here. Same place as L, but we can ignore that for now. We're going to say is 5 equal to the value of the m index? It is. Return, boom. But let's say that this target was actually 4. We would have done everything up until now the same, right? But now we're saying is 4 equal to m? No. Is 4 less than 5? Yes. So now we have to work on this side of the array. And in this case, it's because L and M are in the same location that this kind of looks redundant, but this is what's actually happening in our algorithm. And so in order to work on quote unquote this side of the array, or this half of the array, we're going to do that same calculation where R moves to M plus 1 or minus 1. In this case, it's removing the right pointer. So now R is over here. And like I said earlier, typically how we break out of this binary search is that when L or R crosses over each other, right? So now they're crossed over, we can end the loop. In this case, we would normally return like false or something, but this question wants us to return where the target would normally live in. And in this case, our left pointer actually resides in the index in which this target should have been at. So we can actually return L to return back that index. Hope that made sense. Okay, so let's see what that's going to look like in our code. So we're going to have that left pointer, and right pointer. So we'll have the left pointer in the beginning of the array and the right pointer at the end of the array, which is presented like this. And we're going to say, while we meet that condition, like I said, in a binary search tree is typically when L crosses over R. So while we're not crossed over, so while L is less than R, we're going to run those calculations. And we still want to run it when L and R are in the same location, actually, because that could happen. We're going to want to calculate the middle index, which is going to be what we stated earlier, F plus R divided by 2. And we're going to have that middle value, which we'll keep as a variable because I think we'll be using it more than once. We're going to say if middle or if target equals that value of that m index, then we can simply just return that index. However, if that's not the case, we can say, if target is less than middle, so if target is less than middle, we're going to work with that lower bound of the array. What that means is we're going to shift the R index over to m minus 1, right? And then the other case is going to be if target is greater than middle. That should be the only other case, and that means that L will be moved to where m is plus 1. And then if we ran through this whole while loop with this condition, that means that target wasn't inside of our array. And then we can just return L because, like I said earlier, L becomes the index in which we would have found that target. So let's submit this. And we beat 100 of it, but our memory is lacking. That's all right. That is typically how you would solve this problem. One other thing I want to point out is sometimes you'll see the m calculated like this. And this is because of a very good reason that we don't really have to worry about in JavaScript too much, but essentially this is how you'd be able to calculate it if, let's say, R and L were some crazy numbers, like numbers past 32-bit, right? If you add them together, you'll get an overflow error. And so the idea of doing it this way, it does the exact same thing, is just helps with that overflow. And so by calculating this first, you're actually subtracting those values. And by adding L, which is the lower bound, you essentially achieve the same thing this is doing. So if you see this, just know that it's the exact same thing. It's just helping with an overflow issue. Awesome.